All right, here we're back. Section 2. This is going to be actually the beginning of the chapter, beginning of chapter 10. We're just going to go through 10.1, which is like the introduction, and 10.2, which is going to go over how to represent electrons using dots. And we're going to use dots this whole chapter, so it's a good idea to go ahead and get used to these dots. I've got some artistic dots over there that I'm using just to decorate my walls with, but while I'm here, let me point out what that is. Actually, I even have a model here. So this would be an electron dot diagram for ammonia, which is NH3, nitrogen with 3 hydrogens. Now you see the dots represent electrons, and they represent the electrons that are being shared between the nitrogen and the hydrogen. And you can also see that lone pair of electrons at the bottom not being shared with anything, right? And so here would be another model, a ball and stick model, used to represent ammonia. The blue represents the nitrogen atom, and the white represents the hydrogen atoms. And so there's the molecular formula, NH3. So that was just a model of what it looks like as far as the electrons go. This is also a model of what the electrons, or what the molecule looks like after the electrons are shared between the atoms. And so what's pretty neat about this model kit is there's only 3 holes on the nitrogen, because nitrogen only has 3 valence electrons. And so if I was to try to add another white hydrogen here, there'd be no hole to do that with. So we can use these models to make predictions. Now, could I take this hydrogen off there? Uh-oh, please don't fall off the table. Can I take that hydrogen off and replace it with something else, like chlorine? You bet. Chlorine only has 1 valence electron that it's trying to gain, so this chlorine atom in green only has 1 hole. So I can put that there and I don't have any holes missing. Every hole is filled. So this could totally be a molecule. I don't know what this is, but I'll have to look it up. And this could totally be a molecule. Leave it in the comments below. In the comments below, leave a comment of what this molecule is for me, and I'll give you some extra credit. Homework problems you don't have to do or something. But you see, I can make predictions this way. And large molecules, like this is glucose. This really isn't even that large. We have molecules that are huge, thousands and thousands and thousands of atoms long. Like proteins, for example, are very complex molecules because they're made up of thousands of amino acids long. And the amino acids interact with each other, and the proteins have this really exotic shape. Well, the book opens up with 10.1, kind of telling the story of how HIV protease is an enzyme that HIV needs in order to replicate. And drug companies have found a way to look at HIV protease and look for what's called its active site, where the specific chemical reaction would occur. And they found ways to put something else there, kind of like we did here, so that they would deactivate the molecule, essentially, so that it wouldn't work in the body. And so the person could get HIV, but HIV virus is not going to do anything in the body. Remember, viruses aren't living. They don't reproduce on their own. They need a host to do that. Well, once the HIV gets in the host cell, the HIV virus will not replicate, because the host cell will not replicate that DNA. It will not recognize the HIV protease enzyme, because it'll look a little bit different on the active site. And so that's real important. In fact, that's what pharmacology is all about. Drug companies and people that are even manufacturing plastics and polymers and things like that, they're using chemistry and the shape of molecules to make new substances. And in the body, again, they're using the shape of molecules and enzymes to prevent chemical reactions in the body from occurring, or help chemical reactions to occur when they normally wouldn't. So we can do all sorts of things by manipulating the shape of molecules, because it's the shape of molecules that ultimately end up dictating how they're going to react. Also, knowing what would bond with what. So you see, if I was to just look at this molecule right away, I can tell it's wrong, because this carbon atom has 2 holes here. Carbon likes to bond with 4 things because it has 4 valence electrons. I drew that here, by the way, if you want to look and see. Carbon atom, I drew the dark dots as electrons. The circles they're not filled in, those are electrons that carbon would like to have, because then you'd have 2, 4, 6, 8 electrons around it. And so carbon likes to bond with 4 things: top, bottom, left, and right. But on this one, depending on how you're looking at it, there's just a left and right. And up and down would need to be bonded too to make carbon happy. So this is wrong, and I know what goes here. It's a hydrogen atom and another oxygen atom, which is bonded to another hydrogen atom, and so on. But again, you can look at molecules and make predictions of what atoms are going to bond with what other atoms. And so then you'll be able to recognize patterns. Like, for example, hydrogen only has one valence electron and it only wants another one. So it'll never be in the center of anything. The hydrogens are always going to be on the outside of molecules. They're going to be on the outside surface. So chemical bonding models are very important, and the Lewis structures are by far the easiest structures to make, and so they're just hands down the best. So we're going to study those. So follow me here down the tunnel of doom and into the chapter. We don't need to talk about all this anymore. There are bonding theories that are out there, and it's the Lewis theory after G.N. Lewis. That is Sir Gilbert Lewis, an American chemist, and he's the one that developed the Lewis dot structure. So here's how you do it. Basically, if you were to look at the electron configuration of a substance, for example, this is one for oxygen, you're going to take the highest numbers at the very end. Now, keep in mind that they're not always going to be side by side like this, because you might have a 5 and then a 4 and then a 5. Well, you're just going to circle all the 5s. You're going to circle all the biggest numbers. And in this case, they are right beside each other. So we're only concerned with the highest numbers when we're talking about valence electrons, because valence electrons are always going to be in the highest principal shell number. Another way to remember this, if you want, is that only the S and the P electrons are actually valence electrons. So the electrons, I'm just going to scroll back up here. This might make more sense to you. This, when we talk about the periodic table, remember how it was broken up into blocks? Well, only the electrons in the S block and the P block are going to be considered valence electrons. And that's because when you're in the D block, remember, you have to subtract 1 from the row you're in to know what principal shell number you're in. So just because we're in row 4 here doesn't mean this is 4D. This is actually 3D. This would be 5D. Even though we're in row 6, we subtract 1 for the principal shell number. So D block elements are always going to be just a little bit less, 1 less, and the F block, by example, is going to be 2 less. So D and F, they're never valence electrons. They're like subshells, okay? It's the only valence electrons are always going to be in the P block and in the S block. And 2 plus 6, remember that's all the electrons that can fit there. The S orbital only has 1 shape. It's round. It holds 2 electrons. The P block has dumbbell-shaped orbitals, and there's 3 of them, so 3 times 2 is 6. So it's a total of 6 electrons that can fit in the P block. Well, the 6 plus the 2 is 8. So the octet rule still stands. That's what we're going to be considering when we determine we're determining what these structures are going to be. We're considering the valence electrons, because those are going to be the ones that bond. Sometimes those are called the bonding electrons. But we use that kind of in a different context, so hold on for that. Now, I just said the octet rule still stands, but what we should note is actually there is something called a duet, and the only elements that do a duet are hydrogen only likes 2 electrons instead of 8. It can't have 8 because it's only in the S block. Doesn't have any p orbital electrons, and it doesn't have, and neither does helium. So hydrogen and helium are always just going to want 2 valence electrons. So we'll just say the duet rule. How about that? And basically, the way you show the electrons is you show them one at a time, and you're gonna put one of them on the left or the right. It really doesn't matter. And then you're going to put another one just on the opposite side of wherever you put that first one. And then, so if we put it on the right, the opposite would be the left. And then if you need to show another valence electron, like boron has 3 valence electrons, well then put that one either on the top or the bottom, doesn't really matter. And then put the other one on the opposite side. And then start putting them in twos. And basically what that is showing is orbitals. because each orbital only holds 2 electrons, remember? And so as you go around now, you can just start putting your extra valence electrons with these individual electrons until they're all the way full. So lithium only has 1 valence electron. If you want to be, if you want some structure and you want something to go off of, you can use this. There's a video I'm going to post on Google Classroom of how to draw these that the guy actually uses a little bit different system, so I don't want that to mess you up. But pick a system and stick with it. But basically, you definitely have to put them, like if you only have 1 valence electron, you put it on the right if you're using this system. Then you put the other one on the left, then one on the top, then one on the bottom. Then go back to the right and start pairing them. Then you can pair one on the top, then you can pair one on the side, and then you can pair one on the bottom. You're just going to go around counterclockwise, it looks like. I think the video I post, the guy does the same thing right here, but then he starts making them pair up clockwise instead of counterclockwise. So it really doesn't matter because atoms don't really have a top, bottom, left, or right. It just kind of depends on what angle you're looking at it, right? It's like a sphere. Does this sphere really have a top or a bottom or a side? No. And so again, these are going to represent valence electrons, and valence electrons are what participate in bonds. And we have 2 types of bonds we've studied, 2 types of chemical bonds that we've studied in this course this year, and that is the covalent bond and the ionic bond. And so in the next video, I'm going to do a video on how to use electron dot structures to make ionic bonds and how to use electron dot structures to show covalent bonds. But basically, we're always going to be trying to fulfill this octet rule, which says that in chemical bonding, atoms always transfer or share. Again, transfer if you're ionic, share if you're covalent. They share electrons or transfer electrons in order to obtain outer shells with 8 electrons. So besides the duet, which is 2, most atoms are trying to have 8 electrons in their outer shell. And generally applies to all of your main group elements. Okay, again, except hydrogen and it should be helium, not lithium. Wait. Each of these elements achieves stability when it has 2 electrons in its outermost shell. Yeah, that should be helium, not lithium, by the way. That's a typo. Found a typo. Hopefully you don't come across that and you haven't watched my video because you'll be super lost otherwise. And then let's just do an example. They're real easy when you're just doing elements because you're not trying to show any bonding. You're not showing any bonds, okay? Which only when you're representing compounds where it gets a little trickier. But when you're just showing elements, all you need to know is literally how many valence electrons you have. And so let's say you had for phosphorus. Well, how do you show that? Well, since phosphorus is in group 5A or 15, however you want to call it, it's going to have 5 valence electrons. And you're going to represent those electrons, remember, 1 on each side, top, bottom, left, right. There's 4 of them, and then the 5th one can go with any of these that you put down. It just needs to go with one of them. The book starts here again, and then it goes counterclockwise to continue if you were to add more. But there's only 5 valence electrons, and there they are. That's what it would look like. Okay. If you only have 1 valence electron, that's the easiest. You're just going to have 1 dot, either on the left, the right, the top, or the bottom. So in general, there's 4 sides. There's 4 sides to every element. So you have, if you were to look at this structure here with carbon, you essentially have this orbital. We could say that's the S. You have this p orbital. You have this p orbital and this p orbital. But only 4 orbitals technically can be around an element. So elements can bond with 4 things maximum. But that's not every element. Hydrogen's only going to bond with 1 thing. Chlorine is only going to bond with 1 thing because its orbitals are already full of electrons. There's only one orbital that's missing an electron. So chlorine's only going to bond with 1 thing. But if you could be pretty flexible, carbon's going to be able to be the most flexible. Same with silicon. Silicon also only has 4 valence electrons. It wants 8. So what are you going to do? Gain 4 or lose 4? Neither one. You're going to share with 4 other things. Usually hydrogens, because hydrogens are ready to just share an electron with just about anything. And there's lots of hydrogen in the atmosphere and in our solar system. So hydrogen is a super common element, and it's in a lot of compounds. But this is important because this is going to allow us to tell what shape compounds are going to take and how elements are going to bond to each other. And so I'll see you in the next lecture. Bye-bye.